Okay, so before we get started today, as you all hopefully know by now, we have a midterm next Thursday. Um, so next lecture is also going to be a regular lecture, but Tuesday's lecture is going to be a review lecture. And it looks like Al's also going to schedule a review lecture. One thing to note is the classroom for the midterm is not going to be in here. So I've posted it on the website. It's in Barrows Hall. I think I don't remember the number, but it's definitely posted. So it should not come to you as a surprise that the midterm is not in this room. Also, the homeworks are due today. We have one more homework before the midterm exam. The solutions for this homework are already posted. I just need to enable it. So you'll have access to the solutions right away. For the next homework, you're going to turn it in, and the solutions again are going to be available to you right away. Unfortunately, I'm leaving town Tuesday night, so I will not be here, but Al will be holding a review session and some office hours. So if you have any questions about the solutions, make sure you see him. Okay. We'll talk more about the midterm during the review session. So anybody have any other kinds of questions? Yes.
What's the last lecture that the midterm will cover? Is it this one?
The midterm will cover all the way to this Thursday's lecture. Okay.
Is it going to be an open book exam, or how does it work exactly?
I'll talk about the details during the review session, but more than likely it'll be closed book, and you'll be provided with any equations that you need. Okay.
Provide old midterms or sample midterms?
Yeah, during the review session we'll go through last year's midterm exam. And I'll try to get that to you guys out early, so if you want to try it on your own, you can do it, and then we'll go through it together. Okay? Any other questions or comments? All right. So I have one way to gauge how fast we're going, and that's based on last year. So last year I taught this class on the board, and I didn't have the notes prepared, so it was kind of more extemporaneous. And naturally you go slower when you're thinking on your feet. So this year we're doing about the same pace, except every once in a while we do go a lot faster. So like last lecture was 2 lectures. So if you felt like it was a lot of material, that's normal. If you really do feel like we're going too fast, then you're totally lost. Don't be afraid to step up. I think this is now a smaller classroom. We all kind of know each other. You don't have to be shy. I know most of you guys are really good students, so if you're not getting it, there's something wrong. Okay? Okay, so I wanted to pick up where we left off last lecture. So last lecture, we analyzed basically the noise figure of a 2-port circuit, where we made this simplifying assumption that the input voltage noise and the current noise are not correlated. Okay? So I wanted to revisit that assumption and see basically what happens if we take that assumption away. It turns out it's not that much more difficult to analyze the problem where Vn and In are correlated. So Vn squared, In squared are the equivalent noise, voltage, and current for the 2-port. And it's also interesting to see how many parameters characterize a 2-port. In general, Vn and In are correlated. And what we'll discover today is that correlation coefficient is in general complex. So if you look at the number of parameters, there are 4 parameters that characterize your 2-port. Vn, In, and a complex number. So 4 real parameters that characterize that. Okay? So let's quickly go through the derivation, or maybe not so quickly, of the noise figure of this 2-port, and let's try to take into account the correlation coefficient. So for the moment, I'm going to pretend like these are just normal voltage and current sources, And I could say, well, if they were normal current voltage sources, I can calculate the output voltage, let's say V out here, as, let's find the gain for V in. V in sees a gain, basically Zn divided by Zs voltage divider, right? And then to calculate the gain due to In, we can basically multiply this by, we can find, so this should get multiplied by the voltage gain to the output. To figure out In, I can also calculate the equivalent current, let's say going into Zs. So that would be a current divider times Zs, and now it's a voltage, and then times GV gives me the output signal. So if I group terms here, you can see there's this common factor, Zn over Zn plus Zs. GV is also in common. And then I have Vn plus Zs In. Okay? Now last lecture we did the same exact calculation, but when we calculated the RMS value of the output voltage, we simply assumed that these were uncorrelated. So then we got Vn squared plus Zs squared In squared. This lecture we're going to actually now assume that they are in general correlated. Okay? Any questions up to here? Okay. So I'm going to now play a little trick on you guys. I'm going to say In, the noise current, can be separated into two components, a correlated component and an uncorrelated component. Okay? This is like splitting a vector into two components, a component that's parallel to another vector and a component that's perpendicular to another vector. And the reason that I do that, of course, is now when I take the RMS value here, you can see that the uncorrelated component is going to basically zero out when I take the expected value of V in cross product with the uncorrelated value. The correlated value of the current is just proportional to V in. So it's some complex number. Let's call this YC, the correlation coefficient, times V in. So YC is the correlation coefficient, or correlation admittance. Okay. Now does this trick make sense to everybody, what we're doing? Okay. So the nice thing is now when I calculate V out squared, let's call this just A, right? So that's going to be A squared. This is GV squared, this term here. Now I'm going to get Vn squared. I'm also going to get, now let me write this as, so this can be written here as YC plus Vn, whoops, YC times Vn plus ZSIU, where that's the uncorrelated part. Okay? And this is missing a ZS, thank you. Okay? So now you can see that I can simply sum this term with this term. So now I have the sum of two uncorrelated vectors. So before I do this, let me just write this as Vn 1 plus ZSYC plus ZSIU. And I would like to now calculate the RMS value of this quantity. Okay? And because these two are now uncorrelated, it's just like last lecture. I get A squared GV squared Vn squared, magnitude of 1 plus ZSYC squared, plus Zs squared, magnitude of IU squared. Okay? Any questions? Yes.
And why you don't need to decompose Vn to be Vc and Vu? Is Yc a complex number or it's a real number?
Okay, so in general, YC is a complex number. And the reason I don't need to decompose it is I actually had a choice. I could have either decomposed Vn, and I would have chosen VNC and let's say VNU. So I could have broken Vn into basically components of In, or I could have done the inverse, right? So think of it this way. I have two vectors, and let's say I choose vector A1 as my basis, right? So then I find the component of A1 of A2 in the direction of 1, so that's this component, and a component perpendicular. So this is basically exactly what we've done here. We've broken I into a component that's correlated with Vn and a component that's uncorrelated. So when I take the dot product, the uncorrelated part goes away.
So what is physically IN composed of shell noise, which are totally uncorrelated with thermal noise plus thermal noise.
Okay.
And
We're not talking about any specific kind of noise here. So we're talking about general two-port, right? So if I come back to my general two-port, when I calculate the equivalent current noise, right, it's going to be a linear combination of all the noise sources in this box, right? Let's just for simplicity assume all these noise sources are independent from one another. When I calculate Vn, I also get some other superposition of all the noise sources inside of here, right? So therefore, it's clear that there are components of Vn which are correlated with In, right? Because they arise from the same noise sources. So I can split up Vn into parts that are just a constant times In, and a part that's completely independent from In, right? All right, it's a good question. It's clear. Make sure you understand what we're talking about here. Okay. Any other questions? Yes.
Where does the Vn times 1 plus ZSYC come from?
So here I'm taking the dot product of this vector with itself, right? So then I get the first term, that's this term here. The second term, that's this, and then the cross product term is 0 because they're uncorrelated. Okay. Any other questions?
I guess, why are you taking the dot product of that specific value with itself? That is my original question.
So I want to find the RMS value of the output noise, right? And if these random variables are independent from each other, I can just sum their individual RMS values, right? That's what we did last lecture. This lecture, though, we're saying these two variables that I'm summing are partially correlated. So if I want to find the RMS value of the sum, it's not simply equal to the sum of the RMS values. I have to take into account the correlation. So this is what we've done now. Okay? Okay, those are all good questions. I want to make sure it's clear what we're calculating here. All right, well, now we calculate noise figure. Noise figure is the output noise, the total output noise, divided by the output noise due to RS only. Okay? By definition. And this is a really nice, easy way of calculating the noise figure because the noise due to RS looks a lot like the noise due to Vn, right? So I know that term is going to give me a 1 when I divide out. So if I divide out these terms, these all cancel out because these are in common, this leading coefficient, right? And so what I get is 1 plus Vn squared, 1 plus ZSYC squared, plus ZS squared IU squared, divided by VRS. Okay. Now if you look back to last lecture, if you just make Y correlation equal to 0, totally uncorrelated, you get the same result that we got last lecture. Okay. All right, now it's just like last lecture, we're going to give some equivalent resistances So I'm going to call Rn. I'm just going to assume that the noise Vn is generated by some resistance. I'm calling Rn here. Noise, of course, due to Rs is 4kT Rsb. The noise of this uncorrelated current source, I can say, is 4kT GUB. Okay, and I substitute in these equations, so F becomes 1 plus Rn 1 plus ZSYC squared plus ZS squared, and this becomes GU divided by RS.
The lower the noise figure.
Yeah, basically, that was a good question that Kevin asked a couple lectures ago. Is why does the noise figure, why does the expression not work when RS goes to 0? When RS is equal to 0, there is no source noise. A noise figure is a measure of how much noise you're adding in addition to the source. So if there is no source noise, noise figure doesn't really make sense, right? Because no matter how much noise you add, you get a noise figure of infinity. Okay, what I'm going to do now is simplify this expression a little bit. I can divide through here by ZS squared, so I get F is equal to 1 plus Rn, and then I can call 1 over ZS squared YS squared, so this would be YS plus YC squared plus GU divided by RS. And this actually, when I bring out ZS squared, so ZS is just, let's just say it's just RS. Actually, no, I don't need to make that simplification. Looking at my notes here, I screwed up. This should be GS. Well, let's not trust my notes either. I just did this right before class. I could have made a mistake. So if I divide everything by ZS squared, this would be RS 1 over ZS squared. Okay, so basically what we did last lecture was we noticed that this is a function of ys, and we took a derivative with respect to ys and found the optimal value. Well, now ys is basically a complex number. We're assuming that it has a real and imaginary part, and so what we do is we assume that ys is gs plus jbs. General, it's complex, and we take the derivative of this with respect to the real and the imaginary part, and we solve to find the optimum. Okay, and what you find when you do that calculation is that the optimum value of the source impedance, the imaginary part, is simply the complex conjugate of, it's basically minus BC, where BC is the imaginary part of the correlation coefficient. So we could write the correlation coefficient as GC plus JBC. And we find that the optimum value of GS is GU over Rn plus GC squared square root. And if you look back to your lecture notes, you'll remember that last lecture we found that the optimum conductance was square root of GU, GN we called it last lecture, over Rn. And you see this expression actually matches for GC equal to 0. Okay? The back?
Why do you assume here that YS is complex?
Okay. You don't have to, but it turns out that you get lower noise figure if you take that into account. Okay, that's a good question. Okay, and if you calculate F min, you get a expression very similar to what we calculated last lecture. F min turns out to be 1 plus 2 Rn Gu over Rn plus Gc squared plus Gc. Again, it drops down to the same value as last lecture for Gc equal to 0. And you can write the noise figure in general as F min plus Rn over Gs y minus y opt squared. And again, this is very similar to what we found last lecture. We found exactly the same equation where these were just real numbers. So this tells me that if my source admittance is equal to y opt, I get F min, and as I move away from y opt, the noise increases by this factor Rn over Gs. Okay? Questions? Okay, so this was to satisfy you guys because you're asking questions last lecture about what if they're correlated. If you really don't care, that's fine. It turns out that a lot of times the correlation is artificially introduced. And that goes back to a question that Amin asked last lecture and that I misunderstood. So the question that he asked was, when I calculate noise figure, nothing's correlated because I refer everything to the output or everything back into the input. So I don't even have to deal with the correlation. And in fact, it turns out that this two-port noise theory is very nice, very compact way of understanding the noise of a two-port. But if you're actually ever doing a calculation, it's probably more work to do it this way than just to calculate the noise figure directly. Okay? So let me do an example to show you what I mean. Let's calculate the noise of a FET common source amplifier. Okay? So, very simple calculation. Let me just assume there's RL here. Let me assume I drive it with RS. And I want to find the noise figure of this simple circuit, right? Now, the hard way is to actually find the equivalent two-port representation for this transistor and then to say that's my, then calculate Z opt. That's the long way. Let's do it the short way. The short way is you just draw the equivalent circuit with all the noise sources. So this is RS. We know the transistor has some gate resistance, and that's going to generate some noise, so let's call that VRG. And then we have basically Cin or CGS, VGS. We have C mu, or C gate to drain. And then we have, this is RL in parallel with the RO of the transistor. I have this current here is GM VGS, and then I should add my drain current noise, I drain. Okay, sorry to compress that for you. So if I want to calculate, let me do a low frequency calculation. Make it as simple as possible. So this would be a very fair question to ask you on the exam. Nice and easy question. Calculate the noise figure of common source amplifier at low frequency. Okay? So, hint, pay attention. So let's just calculate the total output noise voltage. So what we do is we take one noise source at a time and refer it to the output, right? So for instance, if I take VRG, then it's going to turn into a current at the output with a gain of GM squared at low frequencies, right? Also, if I take VRS, it also sees a gain of GM squared. And then on the other hand, the drain current just flows directly into my load. So I have I drain squared. Okay. If I assume that those are all the noise sources that I have, this gets multiplied by RL in parallel with RO squared. That's my total output noise. So let me call that VOT. And I assumed that all these noise sources were independent, so I was able to just sum them up like this. Okay.
Is ID the noise generated by RO?
No, remember last lecture we talked about that RO doesn't generate any noise. It's not fictional, it's there, but it doesn't generate noise. The noise is due to the channel resistance, and we call that ID here. Okay. All right, so if this is the total output noise, I also would like to know the noise at the output just due to RS. Well, I've already calculated that. That's just VRS squared GM squared times RL in parallel with RL squared. And then so F is V out total noise squared divided by the noise just due to RS. And I'm writing it out longhand just for you guys, but as you do this a few times, you'll realize you don't even need to write the second expression because it's already there. Simply when you divide, you get a factor of 1. So here, I'm going to get VRG squared plus divided by VRS squared. That's this term. This term gave me 1. And then finally, this term here is going to give me I drain squared divided by GM squared VRS. Okay? So if you look at this carefully, you can see that this term looks like an input referred voltage. So if I had just written this term here, if I had just added another voltage source in series to account for ID, it would have been even a simpler calculation. But this is simple enough. Okay? Does everybody understand this calculation? Any questions? Because this is as simple as it gets. All right. So now let's plug in some values. So VRS is 4kT RS times the bandwidth. VRG is 4kT RG times the bandwidth. Drain is basically 4kT gamma over alpha GM of the transistor times the bandwidth. And I ignored the noise due to the load. I can easily add that on. You can see that the load noise would just add another term here. I won't do it. It's too messy already, so that's fine. Okay, so if I plug in to this equation, I get F is equal to 1 plus RG over RS plus gamma over alpha GM divided by GM squared RS. And I see that this GM cancels out. And so the noise figure is roughly RG over RS plus gamma over alpha GM RS. Yes?
You said you're ignoring the R0 in parallel with RL, right? Or, yeah, you said you're ignoring the noise for that?
Yeah, I'm ignoring the noise for that. Just because I ran out of room. But you can just add another term here.
Okay, but before you said that for R0 there's no noise, but for RL there is, or?
Yeah.
Okay.
Any physical resistor has noise. So if RL is a real resistor that's terminating your amplifier, you have to take its noise into account. Let's say RL is the output impedance of another transistor. Then, instead of seeing RL's noise, you would see the drain current noise of that transistor. Okay? Yes?
But in fact, when you're calculating the noise figure for the amplifier itself, you neglect RL anyway, right? Or
It depends. I mean, if I consider RL to be part of the amplifier and I'm actually interested in the signal noise ratio at the output, then I should include RL. Okay? In fact, you can see that RL is just simply, the noise is just in parallel with this guy, so I can just add it directly on here. So this would be I drain plus IRL. And if I do that, what I get here is an extra term, just GL. So the final answer is going to be GL divided by GM, GMRS, if I include that noise in there. Okay? So what's interesting about this calculation is that you can see that the noise is a ratio of the gate resistance divided by the source resistance, right? And a term that can be made very small by just simply making GM large. So if you believe this calculation, then you could say that if we make GM large, which means increase the current through that device, right, or increase its size, then F basically is dominated by 1 plus Rg over Rs. And so again, we see that Rg plays a very important role. And it's interesting because in analog courses, we just assume Rg is 0. But in this course, we see that Rg is determining the power gain, right? The optimum power gain, the most power we can get out of a transistor. It's determining the maximum frequency where a transistor operates as an active device. And now we can see that it's also limiting how much noise we can get out of our device. Okay? So let's just calculate Rg for a couple of simple cases. So Rg, remember, has two components. It has the resistance of the polysilicon material that is made up of, that basically is that this is just a physical gate resistance material plus some channel-induced component, right? And for a single gate contact, if you do a 117 style calculation, you can show that for a single contact, this resistance is simply 1/3 W over L R poly, the sheet resistance of the poly material, plus the channel resistance turns out to be 1/5 1 over GM, again assuming that alpha is equal to 1. So this is a long channel approximation. So again, you can see that if you make GM very large, this component starts to become negligible, and just the physical resistance of the gate starts to dominate. So this is the limiting noise contributor. Okay. And it's somewhat surprising because it seems like such a trivial thing, right? Let me just draw what our gate is. So let's say I have a transistor, and I want a pretty wide transistor because I want to get a lot of GM out of it, right? So this is my drain and source. So these are my contacts on my drain side and my source side. Right away you could say, you neglected the noise of the drain resistance and the source resistance, and that's true. That'd be another good question I can ask you on the midterm is calculate the noise of a common source amplifier, but include the noise of the drain and source region. Okay? So here's the gate. And so we can see that this resistance is simply this series resistance times 1/3. Okay? And it turns out that if you double contact it, if we talked about this last lecture, or not last lecture, a few lectures back, you can reduce this resistance down by a factor of 4. So I could put another gate contact here, so I could have my signal coming in on both sides like this. This is the double contact. That helps. Reduce it by a factor of 4. But ultimately, if I have a very small channel device, right, if L is very small, you can see this resistance can get pretty large. But let's say, just for example, that my L is 1/4 micron. And let's say I'd like to have a W of 20. So then W over L is 80. and let's say the sheet resistance is 10 ohms per square, right? So then W over L even times 1/12, you see is a pretty large resistance. 800 ohms divided by 12, right? So order of magnitude 80 ohms. Now if I use this limiting value for my noise figure, limiting value is 1 plus Rg over Rs. Rg is becoming comparable with Rs, and so the noise figure is already a bigger than a factor of 2 just because of this gate resistance. Okay. So what's a very simple solution to get around this? Maybe somebody who doesn't know the answer, who's guessing. Anybody want to venture a guess? How can I reduce this gate resistance and still keep the same transistor width? In the back?
Didn't you mention before multiple fingers would help gate resistance?
Yeah, we play the same trick that we played with bipolar. We basically lay out our device as a multi-finger device. So instead of using a wide W, I can use a short W. And then I have basically many transistors in parallel. And I connect all the gates together. And then I basically have I share junctions. So this is my source, drain, source, drain, source. And I can connect all my sources together. And I can also connect all my drains together. Okay. And this actually helps quite a bit because it turns out that it helps by a factor of n squared. So our gate goes down like n squared, where n is equal to the number of fingers. And the reason it's n squared is because I shorten the length of each finger by a factor of n, right? So each resistance is n times smaller, and then I take n of them in parallel. So I get n squared reduction.
Just a short question.
Yes.
When simulating that stuff, for example in Spectre, is there an option where I can say, okay, I'm using 2 contacts because that influences the noise figure and so on?
Yeah, it's basically it's very simulator dependent, and it's also very design kit dependent. So if you're using somebody's process and they call it an RF process, then when you instantiate a transistor, it'll have all these parameters, like basically how many fingers do you want, what's your W, and then it'll go in and try to fit as many contacts as possible to reduce the resistance. So it's very highly dependent on the design kit. In doubt, if you're ever in doubt, you can just put down transistors in parallel. So use the M value, the multiplicity. Okay, you also bring up a good point about contact resistance. It turns out that when you lay out these transistors, you need to make contact to all these polylayers from top metal. So for instance, if I come in from top metal here and I have some contacts, then these contacts actually are quite resistive. They're tiny little plugs that might be 4 or 5 ohms per via. So if I need to go from top metal, let's say metal 6, all the way down to poly, I'm going to have 6 series connections of vias, each on the order of 5 ohms, right? So we're talking 30 ohms per via. I better put a lot of them in parallel to bring that down to a few tenths of an ohm if I don't want it to hurt my noise figure. So all right, well, let's do a calculation. So this was a very low frequency calculation. We already got some insight. Let's redo the calculation at high frequency. Okay? Make sure there aren't any other questions before we do that. All right, so let's repeat the calculation at high frequency. Let's say at medium frequencies. because high frequency always means that your equivalent circuit gets way too complicated, so it's not very pleasant. So here's RS again, here's the voltage source, here's RG again, here's CGS. Again, we're at medium frequency, so we're going to, for simplicity, neglect C mu. If you're really eager to include it, you can just basically use the Miller effect and add a capacitance and basically make CGS artificially larger and C out slightly larger. So this is C out. This is RL in parallel with RO. This is the noise due to RL. Let's just call this the total output noise, which includes the drain noise and RO. And this is GM VGS. Okay, so if I calculate total output noise, it includes the drain noise, the noise due to RL, plus GM squared times the noise of the source plus the noise of our gate times this frequency dependent factor we'll just call zeta, for lack of a better name, where zeta is simply the voltage divider 1 over j omega CGS divided by 1 over j omega CGS plus R gate plus RS. Okay? Or in other words, 1 plus j omega CGS R gate plus RS. And so zeta squared is simply 1 plus omega squared CGS squared R gate plus RS squared. Okay, so now again I calculate the noise F. That would be the total output noise divided by the output noise due to RS only. And I get a factor of 1. And you can see that this factor cancels out for almost all the terms, except basically for these two terms, this cancels out. I don't have to worry about it. It's only these two terms where it comes into play. So I get V gate squared divided by Vs squared, just like before. Plus, now I get my I drain squared plus IL squared divided by GM squared zeta squared. And if I simplify it a bit, I get 1 plus Rg over Rs again. This is going to be gamma over alpha Gm. This is going to be GL. This is going to be Gm squared. This also should have a Vs squared here. Okay. So that's going to give me an Rs. And then I'm going to have this factor. Let me write 1 over zeta squared again. So again, I'm just going to simplify Rg over Rs plus gamma over alpha. Gm cancels out. I get 1 over Gm Rs times 1 plus omega squared CGS squared Rg plus Rs squared. Plus another term, which is GL. Again, I'm going to ignore it. Okay, let's just ignore. Well, the reason I ignore it is if we've got lots of voltage gain in my device, I would make RL relatively large. And so its equivalent current noise is usually going to be small compared to the intrinsic drain current noise. Okay. Okay, so let's now simplify this expression a bit. So I'm going to assume GMRS is relatively large. Okay. And I'm also going to assume that RS is relatively larger than RG. In other words, I've laid out my transistor in such a way so that RG is not big. Because remember, if RG is 50 ohms, your noise figure is already 3 dB. So really, you want to make RG much smaller than RS in a good layout. So if I do that, then I'm going to write this as 1 plus gamma over alpha 1 plus GMRS. And let me call this F infinity, so for high frequencies, times omega squared CGS squared RS squared, where I've neglected the RG term. Okay, so here you could see that I get one RS that goes away. Let me multiply and divide by GM. So now I have CGS squared over GM squared, so this becomes 1 plus gamma over alpha omega over omega t squared GM RS. Okay, so this shows me that in the limit at high frequencies, using the simple model that we just used, the noise is basically strongly dependent on the omega t of the transistor. Okay, so this says that noise goes down like omega t squared, which is in fact very nice because as we scale technology, a lot of bad things happen to transistors, but one consistently good thing that happens is the omega t gets better, right? In the long channel regime, it got better like L squared, 1 over L squared. Even in the short channel velocity saturated regime, it gets better by 1 over L. So today you can go out and buy yourself a transistor with an omega t, an FT, of over 100 gigahertz. So if you're operating at 1 gigahertz, you can see that this term is going to be quite small. And so even though gamma over alpha is larger than its long channel limit of 2/3, so say for a, let's say for L like 130 nanometer device, FT is approximately 70 gigahertz. Gamma over alpha is approximately 2. And so you can see that if you're operating at a gigahertz or so, you can have a really low noise figure device. Now let me just recap a little bit these calculations with what we did earlier. What we did now was we did not use the equivalent current noise and voltage noise at the input and use all that theory. We just simply calculated the total output noise, noted how much of it comes from RS, took a ratio, and that gave us the noise figure. And automatically we didn't have to worry about correlations because we assumed that all the noise sources in the transistor were actually uncorrelated. Now if you've been paying attention, you might say, you made a mistake, because in fact that gate noise has a component that's correlated to the drain current noise, right? That's in fact true. It turns out though that if you take that correlation into account, sure, you'll get a more precise answer. But I found that even if you ignore that correlation and you're doing some back of the envelope calculations, you still get a pretty good match to the real value. So what's kind of a nice way to do the calculations and not have to worry about this correlation, is just to assume that the gate resistance is independent from the channel resistance. Now, of course, the channel component is the one that's correlated, and the gate resistance component is completely uncorrelated, right? That's a physical resistor. But you get a pretty good result if you ignore that correlation. Okay, any questions? All right, so now armed with this new knowledge of noise figure, we can kind of complete our design of small signal amplifiers. So for a small signal amplifier, we basically know how to make them broadband using feedback. We know how to make them narrowband by using inductors basically and tuned networks. We also know how to use matching networks to get the optimum gain. And now we also know how to make them low noise by simply doing an optimum source match. Okay? So given a transistor now, you can go ahead and calculate its optimum gain point, optimum noise point. You can also calculate its distortion, calculate its input IP2, IP3, and you have a fairly complete knowledge of how a transistor is going to behave, or in general an amplifier is going to behave in a given communication system. Okay? And what's particularly interesting is that when we look at noise, noise tells us the lowest signals that we can handle with an amplifier, right? Because if the signal gets smaller than the noise, effectively it gets buried in the noise. Distortion tells us what the largest signals are that we can handle. And so if I take both into account, effectively I learn the dynamic range of my amplifier. Okay? So let me draw a couple of pictures. So let's say that I look at the output spectrum of an amplifier for a very small signal, and I see something like that. So, and let's say this signal, say I make it a little bit bigger, let's say this signal is like 10 dB above the noise figure, right? Let's say that I know that I need a factor of 10 more signal power than noise power in order to figure out the information in this signal in the presence of noise. Okay, so that's a system spec that you'll be given. So this pretty much tells me P min, the minimum signal that I can put into this amplifier and still get useful information out, right? On the other hand, if I now put in a really large signal, let's say I put in 2 large signals, the noise floor is higher, right? That's because the amplifier has some noise figure. So the noise, this is due to the noise figure of the amplifier. The growth, not the amount of growth, right? It's the degradation of the noise figure that tells you what the... so actually, the way I've drawn it, it looks like the SNR is better in this case, but it's not. Anyhow, the important point is that these distortion products begin to compete with your signal. Like these are the IM3 distortions, the IM5 distortions, the IM7 distortions. And these distortion products, you know, for two very tones that are very close to each other, all fall in band. You can think of a modulated signal as having an infinite number of tones. And so all this distortion is going to fall into your band and mess up your spectrum. So if you make the requirement that your signal has to be a factor of 10 bigger than these distortion products, like you did in this last homework assignment, this also tells you P max. This is the maximum power that this device can handle. P max is given by the distortion characteristics. P min is given by the noise characteristics. And the ratio of P max to P min is the spurious free dynamic range of the amplifier. Okay? So this should bring all the concepts that we've learned in this class all together. You can see now you have a very nice understanding of the properties of amplifiers. All right. Any questions up to here? Okay, so let's start looking at designing LNAs. Remember, an LNA is a low noise amplifier, and it's usually the first block that we have in a communication system. So communication system front end looks like this. We have an LNA, and the job of the LNA is to reject the noise of the rest of the system as much as possible. Remember, the noise figure of the entire system is the noise figure of the first stage, so the noise figure of this LNA in this filter, plus the noise figure of the rest of the system minus 1, the noise factor of the rest of the system minus 1, divided by the gain of the LNA. So the LNA has two parts. It should have gain to reject the rest of the noise, and it itself should have low noise. Okay. The other thing that we'd like to get out of a LNA is a good impedance match. And the reason we'd like to get a good impedance match is, of course, we'd like to transfer as much power as we can into our LNA, because basically, you put it up an antenna, you're receiving a weak signal. You don't want to lose any of that signal if possible. There's another reason why we like to have an input impedance match, and it's slightly more complicated. It's related to 117. The reason is that usually there's a transmission line from the antenna all the way to the input of the LNA. That might be a physical cable, or it might be just a short section on a PC board. And that transmission line will take the input impedance of that LNA and transform it to some value. Now, if you have an impedance match, in other words, the input impedance of the LNA is equal to the characteristic impedance of that transmission line, then at all frequencies, the antenna sees constant impedance. So that guarantees that I'm always going to transfer a given amount of power from the antenna to my LNA. On the other hand, if this is not matched to basically the characteristic impedance of the transmission line, then the input impedance is kind of unknown because it depends on the length of that transmission line and its characteristic impedance, 1, and 2, it varies as a function of frequency. So then the amount of power that I transfer depends on frequency, it depends on how you lay out your board, everything gets complicated. So what people do is they don't want to have to tell their customer, well, you have to put down the LNA and then you have to have 1 inch of transmission line with this characteristic impedance, and if you have a bend in the transmission line, put an extra capacitor here. And basically they want to say, yeah, this amplifier is matched to 50 ohms. Go ahead and connect it to a transmission line that's 50 ohms. It can be as long as you want. Of course, the longer you make it, the more power you'll lose, but ultimately, irregardless of frequency, you're going to get a certain amount of power into your LNA. So having an input match is very convenient. Okay? Now the reason I bring this up is because it's a very controversial topic. Almost anybody who takes an RF course at some point says, why do I go through all this trouble to match the input impedance of an LNA? Let's say I'm willing to give up a little bit of power gain and not put a matching network down. Makes my life so much easier. Why not do that? Well, that's one of the reasons why you need to match the input impedance of an LNA. Okay? So what are the simplest ways of matching an LNA? And actually quite common is just an input termination. In other words, if I take this common source amplifier that has very good noise performance, as we've already seen, at low frequencies or at moderate frequencies, Zin is 1 over j omega CGS, right, or effective CGS, because the Miller effect, which is basically large if the device is not too big. In other words, it looks like an infinite input impedance. So in order to get an input match, all I need to do is put a resistor down of value Z0, right? And this could match, let's say, a transmission line. It's cable coming in, which is characteristic Z0. This is nice for several reasons because I get a broadband match, right? As long as this resistor acts like a good resistor, I'm going to get a match to this Z0 over a broad range of frequencies, assuming this device doesn't come into play, right? And so what's the problem with doing this, right? Why not just do this and be done with it? Okay.
Yeah, the additional noise of the resistor, probably.
Yeah, how much does that noise really hurt us?
It's a factor of 2, right?
Yeah, it's a factor of 2, because if I now ignore the noise, let me assume that this transistor is noiseless. then I have an equivalent circuit that looks like this. This is VRO squared. This is RO. This is RS, which is also RO. It also has a noise source of VRO. And so if I look at the noise coming into my circuit, it's double the noise of the source. So the noise factor F is going to be 1 plus basically the equivalent noise divided by the noise of the source. And we just found the equivalent noise is also equal to the noise of the source, so it's going to be bigger than 2. So in dB, F is bigger than 3 dB right off the bat. Okay. Now, 3 dB noise figure is not terrible. It's not great. You know, if you have a good amplifier, you can get down to really low noise figures of, let's say, 1.1, 1.2 dB. So you might say, yeah, it's not the best thing in the world, but it's still pretty damn good. 3 dB, hey, I'd be happy if I got a noise of 3 dB. But we neglected the noise of this transistor, right? That's also going to add. So now maybe it's 4 dB. And then, unfortunately, in real life, your noise figure is always larger than this by the attenuation at the input of your device. So let me just talk about that briefly. Let's look at the noise figure due to an attenuator. Okay, and you could say, well, why would you put an attenuator in your system? Well, unfortunately, you always end up with an attenuator because you put in a filter. So all communication systems, or nearly all communication systems, need a filter to reject all the out-of-band interferers, right? You guys looked at homework number 4, the AM radio station, and you looked at just how many interferers you had just in the AM band. Now imagine that there was no filtering at all, so you picked up broadband signals all over. You can imagine that many, many, many combinations of signals, 2 tones, 3 tones, 5 tones, 110 tones, could combine in some nasty way to mess up your amplifier. So the simple solution is just put a filter to get rid of all those band interferers. So if I have a system like this, and this is my LNA, and let's say my LNA is matched to 50 ohms, okay, and let's say this is a 50 ohm filter. In other words, it's designed so that the input impedance is 50 ohms. And let's say that unfortunately this filter has an insertion loss of 3 dB. Okay, just for example. So the question to you guys is, what's the noise figure of this filter? Okay. So without doing any math, I'd like to convince you guys that the noise figure of this filter is exactly its insertion loss. Okay. And does anybody see why that is?
Because the gain of the filter is minus 3 dB, so the noise of the output and input is minus 3 dB, of course.
So the gain is 3 dB, but why is the noise?
The noise is fixed, but the signal gets down 3 dB. So
Exactly. So if I look back in here, the source impedance is also 50 ohms, right? In other words, the noise power, the way to think about this problem is that the amount of noise power that you have is KTB, right? Where K is a fixed number in an impedance matched environment. So this filter hasn't done anything to change the amount of noise. It hasn't actually attenuated the noise. It's just attenuated my signal. Okay? So let me explain that in a little bit more detail. So if I look back here, the available noise, let's say voltage, is 4kT RS times B, right? If I look over here at how much noise power is available, it's also really proportional to the real part of the input impedance looking in here. Because the real part of the input impedance is also 50 ohms, the amount of noise that's available from the source is the same as the amount of noise that's available from this attenuator, right? But my signal is 3 dB smaller. So by definition, the noise figure of an attenuator is equal to a matched attenuator is equal to its insertion loss. So noise figure of some component that has a certain insertion loss is equal to its insertion loss. So in this case, it'll be 3 dB. Okay. Any questions about that? this is a little confusing to digest, so I recommend that you think about it and come to office hours if you have questions. Kevin?
Just to make sure I'm understanding this, the noise from the source also it gets attenuated, but there's more noise from the filter.
Yeah, that's a good way to think about it. The noise from this guy is getting attenuated, but it's adding its own noise. At the end of the day, you end up with the same amount of noise that you started with. Okay. Other questions? All right, so that means that when you put together a system, coming back to this original noise figure of 3 dB, you might find that it's too high. Because if you take into account the fact that the transmission line has some insertion loss, right? This is going to be some trace on a PC board like FR4 that has some insertion loss. You're going to put a filter in there, that's going to have some insertion loss. At the end of the day, you're going to find out that you're going to have a few dBs of loss to add to the noise figure of the LNA. So if this is 3 dB and you add another 3 dB and you're to 6 dB, and then you add the noise of the transistor plus the rest of the circuit, pretty soon you're up to a noise figure well over 10 dB, and that's unacceptable. So in order to maximize the communication range, remember, you have to minimize the noise figure of your system, going back a couple lectures. So typically we'd like to have noise figures that are less than 2 dB. Okay? So something simple like this is very elegant and simple, but unfortunately the noise figure is just too high. Okay, well, another way to get matching from a transistor is to use a common gate device. So how about a common gate LNA? Again, common gate device is really nice because the input impedance is approximately 1 over GM at low frequencies, and I can basically design it so it's equal to Z0. Right? Pretty simple. And then I connect RS, and I want to now calculate the noise figure. So again, this is a good question to ask you guys on the midterm. Calculate the noise figure of this simple circuit. In fact, I encourage you guys to go home and try it. We're going to calculate it using a simple trick. Let's just take into account the drain noise. So let's just say just take into account this noise. Okay? In other words, I can break up my circuit. What I can do is I can take this current source and break it up into two current sources in series. Let's say connected to ground. Okay, this makes the analysis a lot easier. This is IRS. This is I drain. This is I drain. And this is RS. Okay? So this is just a simple transformation of this circuit here. And now I'd like to calculate the noise figure of this circuit where I assume that this is noiseless. Okay, and again, let's do this at low frequencies to keep the analysis simple. All right, well, again, I want to make things as simple as possible. For a moment, forget the fact that you have this noise here. Just focus on this noise. You can see that if this were the only noise in the system, the noise figure would be basically the ratio of these 1 plus the ratio of these guys, right? Because they're competing with each other. So it would be, the noise figure would be 1 plus I drain squared divided by RS squared. Okay? In other words, it's 1 plus, so let me say greater than. We're finding a lower bound on the noise figure. So the drain noise is 4kT gamma over alpha 1 over GM divided by 4kT RS times B. GS, excuse me. Of course, the 4 kTs cancel out, and I get 1 plus 1 over gm times gs. Sorry, this is gm, so this is gm over gs. And because I have an impedance match, gm is equal to gs. So that means that f is bounded by 1 plus gamma over alpha. Of course, it's going to be larger because we've ignored a lot of noise sources here. But already you can see that this is also unacceptable because gamma over alpha is approximately 2 for a short channel device, so that f is already 3. So common gate amplifier is again a very nice way of getting an impedance match at low frequencies, but its noise figure is unacceptably high. Okay. Any questions or comments? All right, well, how about using matching networks? So an LC matched LNA. Again, we go back to this nice common source amplifier, and we say, okay, it has a really good noise performance, but basically Z in is roughly 1 over j omega CGS prime, and that's not good. It's not a power match. So what I'd like to do is put in a matching network here. Let me put in our gate here as well. I'd like to have a matching network, so this could be a pi matching network, a L matching network, or some arbitrarily matching network. That transforms this to RS, or let's just say in this lecture Z naught. Okay. So what are some of the issues with designing this matching network? This is something you could do. There's nothing wrong with this approach. Biasing? Sure, yeah, but actually I can use the matching network to do some biasing for me as well, right? I could forget about biasing now. It's not an issue, let's say. Well, the only issue is if you make this a low noise device, RG is going to be pretty small. It's going to be a few ohms, maybe 1 ohm, 2 ohms. And you're trying to match the Z naught, which is typically antenna impedances. It might be 75 ohms, 300 ohms, 50 ohms. There's quite a bit of range that you need to go. So you have, let's say, 50 ohms to 1 ohm as one example. So remember, the Q of your network is proportional to the square root of R high over R low minus 1. So if you have a 50, your Q is going to be roughly square root of 50. Roughly 7. And remember, the insertion loss of a matching network is roughly 1 over 1 plus Q over the unloaded Q of your component. And it turns out that if you're building this thing on chip, it's pretty hard to get component Qs better than, let's say, 5. So if it turns out that your component Q is 5, and you need to do a matching network, your insertion loss is going to be pretty high. It's going to be more than 3 dB. So all of a sudden you're back to square one. You have this large insertion loss from your matching network, and that's going to basically kill your noise figure. Okay. So then you say, let me try a 2-stage matching network. You could play games. Maybe you reduce the insertion loss down to 2 dB, but you're still stuck. You have this big loss in front. And you definitely need an impedance match, because remember, you're trying to design a component that terminates a transmission line. So you'd like to have a constant impedance versus frequency, or at least in the band of interest. Okay. Well, somebody at some point figured out a nice tricky way of matching a device like this, and it was actually a very practical way. So the idea is that if I actually interface my amplifier to the external world, I'm going to get